Hi there! Operational amplifiers, or in short opamps, are encountered very often in analog circuits to make amplifiers, filters, comparators, and oscillators. They are widely used for the simplicity that can be obtained in the design of circuits, but also for the advantages of improved stability, precision, and at times linearity that can easily be obtained. All these advantages come from the hidden complexity of their own design, that allows us to build the same complexity in our circuits while keeping them simple, because we don't have to deal directly with that complexity. Today, we will go through a high-level description of the opamps, and we will see how we can use them to make several simple circuits with exceptional features. Before diving into the details, please take a few seconds to subscribe to this channel and to click on the bell icon to receive notifications when new videos are published. The subscription will also help in making this channel grow and serve you better. And now, let's begin! An op-amp is an integrated circuit that is very complex on the inside, but at the same time very easy to use. Here is the electrical symbol. It has two inputs, one marked with a plus and the other with a minus. These are called the non-inverting input and the inverting input. We will see why very soon. These devices are usually powered with two separate voltages, both measured against the ground. Powering them this way allows us to deal with analog signals that can be both positive and negative with respect to the ground, without the need of use capacitors to decouple these signals from DC. The op-amp is basically a voltage amplifier, but its gain, or the ratio between the output and the input voltages, is very high. Depending on the particular IC we'll work with, it can easily go from values of 100,000 to several millions. Because of these high values of gain, we can approximate our calculations assuming that the generic op-amp has an infinite gain. Also, both plus and minus inputs of the op-amp have a very high impedance, so we can safely say that when we connect a voltage source to any of the input, there will be no current flow. Thanks to these properties, op-amps are able to amplify signals extremely small, and to avoid bringing them into saturation, we usually need to put them in a circuit with a strong negative feedback to limit the gain to reasonable values. Because there are two inputs, and because the output depends on the difference of these inputs, they are applied very often in circuits where it is necessary to provide a strong noise cancellation. Here is a picture of the inside of a typical op-amp. You can see that it was no joke when I told you that they hide a very complex circuitry on their inside. But we are here not to talk about their inside complexity, but to talk about the simplicity with which they can be used. So let's start examining some of their applications both on paper and in the lab. Let's start by drawing the symbol of the op-amp, then let's connect the non-inverting input to ground. The inverting input is connected with a resistor RF to the output and the resistor Rin to the input voltage. The RF resistor is the one that provides the feedback to the amplifier, and since it is connected to the inverting input, this is the negative feedback. Negative feedback means that part of the output signal is sent back to the input and then it is inverted 180 degrees, so it will be subtracted from the actual input signal. Now, because the op-amp has an infinite gain, the voltage between the plus and minus inputs has to be about the same. In fact, it is the difference of the signals on the two inputs that it is amplified with the op-amp gain and sent to the output. Only if the two inputs are about the same, the output will make sense, otherwise the output will just go into saturation and will not be useful to us. But since the two inputs need to be almost at the same voltage, and since the non-inverting input is connected to ground, the voltage at the inverting input must also be about 0 to be equal to the one on the other input. So even if the inverting input is not connected to ground, it has its same voltage level, so it is like it was connected to ground too. We call this condition as virtual ground, and we say that the inverting input is at virtual ground. This is an important fact because it will help us in the calculations for this circuit. Since the minus input is at V equals 0, the current In inside the resistor Rin will simply be Vin over Rin, and similarly, the current If through resistor Rf will be Vout over Rf. Both In and If go toward the node at the minus input, and since there is no current going out, it means that the two currents In and If must be opposite, so If equals minus In. Substituting with the values of currents we calculated earlier, we obtain that Vout over Rf equals negative Vin over Rin, and rearranging, Vout over Vin equals negative Rf over Rin. So the amplification of this circuit, Vout over Vin, is simply obtained by the ratio between those two resistors, and the output voltage will have an opposite sign than the input voltage. And that's why this circuit is called an inverting amplifier. Let's now test this circuit in lab using a general purpose opamp, in this case an LM741, and resistor values of 15K for Rin and 75K for Rf. Based on these resistors, the amplification should be 75 over 15 equals to 5, and the output voltage should be the reverse of the input voltage. Let's see if it is true. Here is the circuit assembled on a breadboard. The input is a sine wave coming from a function generator, and we can see both the input voltage and the output voltage on the oscilloscope. The input is the yellow trace, which is 500 mV. The output is the blue trace, which is 2.5 volts. And also the output is the opposite as the input, as we expected. Let's start again with an opamp. This time we attach the input voltage to the non-inverting input. The inverting input is attached again to the output through a resistor R2, and it is also attached to ground through resistor R1. R2 and R1 make up the negative feedback circuit of the opamp. Because there is no current flowing in or out the inverting input, we can safely say that V-, the voltage applied to the inverting input, is given by the output voltage Vout going through the voltage divider made of R2 and R1. So V- equals Vout times R1 and divided by the sum of R1 plus R2. We also know that the voltage of the two inputs must basically be the same, so V- must be equal to V+, and also V+ is the same as Vin. Therefore, we can write the following, that Vin equals Vout times R1 and divided by the sum of R1 and R2, which can be rearranged this way. And so we can say that the amplification of this circuit equals the ratio between R2 and R1 plus 1, just 1 point higher than the case of the inverting amplifier, but still depending only on the two resistors R1 and R2. Let's see in the lab how this plays out. We are going to use for R1 and R2 the same values of the corresponding resistors in the previous circuit, 15K and 75K. Because of that, the amplification of this new circuit is supposed to be 6 rather than 5, and since there is no minus sign in the formula, the output voltage will have the same phase as the input voltage. No inversion this time. So here is the circuit on the breadboard, same input sine wave, and the oscilloscope here shows the same entities as before, the input signal in yellow and the output signal in blue. Note how the output signal has now the same phase and how its peak-to-peak value is now 3 volts instead of 2.5. The voltage follower is one of the two easiest circuits that can be created around an opamp. In fact, there are no components directly associated with this functionality, just the opamp. To draw the schematic for this circuit, we start once again from the opamp, then we connect directly the output with the inverting input. And that's it! we use the non-inverting input as the input of the voltage follower, and the op-amp output is of course the output of the voltage follower. How does it work? Well, simply put, we apply the whole output signal back to the inverting input, obtaining the maximum possible negative feedback, which translates in having an amplification of only 1. So basically, whatever is the signal applied to the input, we find exactly the same signal at the output. Now you may ask, why do we care? We already had that signal, why don't you use that directly? Well, the answer is impedance. When we put a voltage follower in between two other circuits, we do what we call an impedance adaptation. We adapt the impedance of the circuit at the left of the voltage follower to the impedance of the circuit at the right. Let's put it this way. Let's say that we have an oscillator and we want to use its output to drive another circuit that is going to draw from the oscillator a certain amount of current. Unfortunately, if we draw current from the oscillator, it will stop oscillating. The solution is to put the output of the oscillator as input to the voltage follower. Given the high impedance of the op-amp input, we will not draw any current from the oscillator. Now we can use the output of the op-amp, which has the same signal as the oscillator, to draw the current we need, which is possible because of the very low impedance of the output of the op-amp. Let's now take a look at how this circuit works with a simple lab experiment. The circuit we will use is very simple. We have an op-amp on the breadboard and the output pin is connected to the inverting input pin. A function generator is connected to the non-inverting input of the op-amp, and this is the oscillator in our previous example. The oscilloscope shows on the yellow track the input signal and on the blue track the output of the op-amp. You can see that the two signals are identical. And here is the other simple circuit that can be created with an op-amp. There it is, nothing else. Not even the negative feedback connection. Well, what's going on here? Simply put, with this circuit we want to actually exploit the extreme gain of the op-amp, bringing it into saturation. That's why there is no feedback. We just put a reference voltage on the inverting input. Then we put a signal to the non-inverting input. What we want to achieve is to be able to say when the input signal of the non-inverting input is higher or lower than the reference voltage. And in fact, when the input signal is greater than the reference voltage, the op-amp will saturate and will output the maximum possible voltage, which will be just a little less than the positive voltage provided by the power supply. Vice versa, when the input signal is lower than the reference voltage, the op-amp will saturate again, but in the opposite direction. It will output the minimum possible voltage, which is very close to the negative voltage provided by the power supply. We can consider, for example, the positive output as a logical 1 and the negative output as a logical 0. So we will have an output of 1 when the input signal exceeds the reference voltage, and we will have a 0 otherwise. To test in lab this behavior, I will attach to the inverting input a potentiometer connected like this. This will allow me to change the reference voltage to show how the comparator will change its response to the input signal. Let's check this out. So, this is the op-amp, and this is the potentiometer I am using. Right now it is set to provide a voltage of 0 to the inverting input. The usual function generator is attached to the non-inverting input. The oscilloscope shows in yellow the input signal and in blue the output signal. You can see that the op-amp jumps from positive to negative voltage depending on the level of the input signal. And since I have the reference voltage to 0, the output goes high on the positive part of the sine wave and negative otherwise. But now, if I change the reference voltage, you can see that the amount of input signal higher than that becomes smaller or higher, and so the length of the ones and zeros of the output signal changes accordingly. Let's now make an example of a current generator. Here is the usual op-amp, and here are now two resistors, RL and R. RL is the load through which we want a constant current. To obtain that, we simply need to send a negative feedback to the op-amp inverting input, which is the voltage in between the two resistors, like this. Let's see how this works and how we can calculate the amount of current we need. The voltage of the inverting input V- depends on the output voltage Vout, reduced by the voltage divider made by the resistors RL and R. So we have V- equals Vout times R divided by the sum of R and RL. At the non-inverting input, we have V plus equals Vref, which is a reference voltage. The output current is given by V out divided by the sum of R and RL, since there is no current going through the wire towards the inverting input. And since V plus and V minus they have to be almost identical, then we can say that V out times R divided by the sum of R and RL equals Vref, which we can rewrite this way. So now we can substitute V out in the current equation, and we obtain that I out equals Vref times the sum of R and RL divided by R times 1 over the sum of R and RL, which is equal to Vref over R. So basically the current depends only on the values of the resistor R and the reference voltage. Even if the load RL changes, the current will not, so we have a constant current going through the load. In addition, if we want to change the value of the current, we just need to change the reference voltage without touching anything else, since the current is directly proportional to Vref. To show this in lab, I made a circuit like this one, where I just used a potentiometer to generate the reference voltage, and where I put an ammeter in series with the load, so we can measure the current flowing through it, which is the resistor of 10 ohms. Let's see how this works. Here is the circuit mounted on a breadboard. You can easily see the load mounted on the output, which is pin 6, which is also connected to the alligator clip that goes to the ammeter. The ammeter is currently showing an amount of current of 0.77 mA. And now you can see how, acting on the potentiometer, I can change the value of the current, and I can have either a negative or a positive value of it, depending on the sign of the reference voltage alone. Another interesting circuit to analyze is the voltage adder. Algebraic operations are actually the reason why the opamp has its name. It was originally designed to perform mathematical operations analogically. Of course, that was before the advent of the digital circuits. Let's take a look at the adder circuit. We have the opamp with a negative feedback given by the resistor RF. The non-inverting input goes to ground, and the inverting input is connected with a number of inputs via resistors that have all the same values, which we identify with R. At each input we have a different voltage, Vin1, Vin2 and Vin3. Let's see how this circuit works. First thing to notice is that since the non-inverting input is connected directly to ground, the inverting input itself is at the virtual ground. That said, we can calculate current IF going through the resistor RF as IF equals V out over RF. And similarly, we can calculate the current across each resistor R as I1 equals Vin1 over R, I2 equals Vin2 over R, I3 equals Vin3 over R. Since there is no current going toward the inverting input, it has to be that IF equals the opposite of I1 plus I2 plus I3. And, because of the previous equations on the current, we can now write that V out over RF equals negative Vin1 over R plus Vin2 over R plus Vin3 over R, which is equal to negative 1 over R times the sum of Vin1, Vin2 and Vin3. So now we can calculate the value of V out, which is negative RF over R times the sum of Vin1, Vin2 and Vin3. So the output is proportional to the sum of the three voltages and the three inputs, but with a reversed polarity. If we use a value of RF equals to the value of the resistors R, the output voltage is exactly equal to the negative of the sum of the input voltages. We can easily test this in lab with the same circuit we just analyzed. I will use the voltage of 3 old batteries for the inputs, so to obtain 3 slightly different values that we can easily add to verify that the circuit worked correctly. Let's do it. You can see that there are 3 input resistors in the circuit and 1 feedback resistor, all of the same value. There are also 3 alligator clips attached to the 3 inputs, and those come from the 3 batteries. Let's measure the voltages of the 3 inputs. The first one is 1.187 volts. The second one is 1.190 volts. The third is 1.227 volts. The sum of these voltages is about 3.6 volts. If we measure the output voltage, we obtain just that, 3.6 volt, so the adder works perfectly, not considering, of course, the tolerances to the resistors used, which are not perfectly equal to each other. An important circuit built around the op-amp is the differential input amplifier. Here is its schematic. First, we can see that the feedback resistor R is connected between the output and the inverting input, as usual. Then there are two input resistors and a fourth resistor that is connected between the non-inverting input and ground. All the four resistors have the same value. Once again, and this is very important for this circuit, remember that the values V plus and V minus have to be about the same, or V plus about equal to V minus. Since I'm sure by now that you are bored of watching one calculation after another, let me just put here the formulas without much saying. I'm sure that those of you that want to go through the details can do that from these equations. Let's just take a look at the final results now. That tells us that the output voltage is exactly equal to the difference of the voltages applied to the two inputs. Yes, exactly. This is the opposite of the previous circuit. That one was adding voltages. This one, instead, is subtracting them. Let's see how this happens experimentally now. So, this time we have two inputs, connected each with a different battery. Let's measure the voltage of the first input, which is 1.188 volts. And let's measure the voltage of the second input, which is 1.230 volts. The output should therefore be 0.04 volts or 40 millivolts. Let's see what the voltmeter measures at the op-amp output. That is about 35 millivolts, which is within the tolerances of the resistors that I have used. All good then. So far, we have seen different circuits providing different features, but all using resistors to do that. However, where the op-amps starts to excel is when we start using reactive elements like capacitors and inductors. The most general form of an op-amp circuit with reactive elements is the one in this picture. It looks like the inverting amplifier we previously saw, but this time it uses impedances instead of resistors. The amplification of this circuit can be calculated the same way as the inverting amplifier, but the formula now assumes the form A equals V out over V in equals negative ZF over Z in. Depending on how ZF and Z in are implemented, the behavior of this circuit changes radically. This is the basis for building what are called active filters. This is a huge subject in the operational amplifiers theory. Here I will just show you three of the most significant examples: the integrator or low-pass filter, the differentiator or high-pass filter, and the bandpass filter. Let's dig into that. The integrator is obtained using a capacitor as the ZF and a resistor as the Zin. Its amplification is therefore dependent on the frequency and can be expressed by the following formula. In here, the cutoff frequency is Fc equals 1 over the product of 2 pi Rin Cf. Basically, as long as the frequency of the input signal is lower than the cutoff frequency, the output signal reflects the input signal, although it will be out of phase. Once the frequency of the signal approaches the cutoff frequency and goes beyond, the amplitude of the output signal becomes smaller and smaller, and that's because the negative feedback becomes greater and greater. We can represent this behavior drawing a diagram of the output voltage with respect to the frequency, which gives us something like this. And that is why this circuit behaves like a low-pass filter. Low frequencies go through, high frequencies are attenuated. Another way of showing how this circuit works is by looking at how the output voltage behaves with respect to the input voltage. To simplify things, let's assume that the input voltage is made of a square wave. During the positive interval of the square wave, the output voltage is initially negative, but then the capacitor CF starts charging, and the result is that the output voltage starts increasing. During the negative interval of the square wave, the output begins with a positive value, and then it starts charging capacitor CF in the opposite direction direction, so this time the output voltage starts decreasing, and then the cycle repeats. The triangular shape of the output resembles the mathematical integral of the square wave, and that is why this circuit is called integrator. Let's take a look at the integrator behavior in the lab. Once again, the circuit is built on a breadboard and a function generator is used as the input. This time, rather than using a sine wave, I have used a square wave. Note how the output signal is modified by this circuit. The differentiator works exactly the opposite way of the integrator. First, ZF is replaced with a resistor, while Zin is replaced by a capacitor. Here is the amplification of the circuit. The cutoff frequency has exactly the same formula as the integrator, but this time the behavior is different. When the input signal has a frequency higher than the cutoff frequency, the capacitor has a very low reactance, which translates into an output signal of similar amplitude to the one of the input. When the frequency of the input signal goes below the cutoff frequency, the capacitor has a high reactance, which translates in a lower amplification, and therefore the signal amplitude becomes smaller. A diagram of the output voltage as a function of the frequency shows exactly that. And this is of course the behavior of a high-pass filter. If we input a square wave into the circuit, a high voltage will initially go into the inverting input, but then as the capacitor charges, the voltage becomes smaller and smaller. And this happens for both the positive and negative parts of the square wave. Of course, the output will be positive or negative accordingly. The shape of the output signal resembles the one of the mathematical derivative of a square wave, and that's why the circuit is also called the differentiator. Let's take a look now at how a practical circuit responds to signals of different frequencies. The circuit is similar to the one of the integrator, but the resistor and the capacitor are switched around. I am also using a sine wave to show the effect of the frequencies on the output signal this time. As you can see, when the frequency goes down, so does the amplitude of the output signal. The last circuit I want to show you is the bandpass filter. If you look carefully, you will see that this circuit has both the characteristics of a low-pass and a high-pass filter. R1 and C1 make the circuit behave like it was a high-pass filter, but R2 and C2 make it behave like it was a low-pass filter. And in fact, if we merge the diagrams of the low-pass and high-pass filters, we obtain something like this. And this resembles the diagram of a circuit which gives precedence to a specific frequency and attenuates everything else. This is why this is called a passband filter. Let's examine it in the lab. The cutoff frequency of this circuit, with the components I used, is 900 Hz. Look how the output signal becomes smaller when I decrease the frequency, becomes higher again when I increase it, and then it starts lowering again when the frequency becomes higher and higher. The maximum amplitude of the signal is just at the cutoff frequency. Operational amplifiers are very versatile components to use for everyday projects involving analog circuits. The applications we have seen today are just the tip of the iceberg, because there are infinite circuits that can be built around this device. Today, we went through a high-level description of what an opamp is and some of the very basic circuits that can be made out of it. I really hope you enjoyed this tutorial, and please feel free to post questions in the comments if you want to know more. I will try to answer as much questions as I can. Thank you for watching this video, and please give it a thumb up, which will help improving its visibility so others can enjoy it too. And finally, don't forget to subscribe if you haven't done so already, so you can be automatically notified of new videos. A small monetary contribution will also help me in making more and better videos for your enjoyment. Details are in the description below. See you on the next video, and as usual, happy experiments!